In this example for a beam with 2 point loads and 1 UDL, first of all I'm going to show you how to draw your free body diagram, and then we're going to use the three basic equations for statics, essentially all the forces in the x direction, all the forces in the y direction, and the moments about any point must add up to give you 0, and we're going to use that to solve for the reaction forces, which in our case will be VB, HB and VE. We're going to start this problem by first of all drawing a free body diagram. In this, we're going to replace the supports with the associated forces, and if we have any weights or loads, we apply them with the correct force applied. In this case, we've got 2 point loads and 1 UDL. They are already in kilonewtons as a load, so we don't need to change them. So we would draw our beam again, put on our weights, loads that we have. So we have 2 point loads and 1 UDL. For our 2 kilonewtons or 8 kilonewtons, and the UDL is 6 kilonewtons per meter. Then for the support, fixed support at point B, we replace that with 2 forces, label that VB and HB for the vertical and horizontal, and at point E the rotor support gets replaced by one force called VE. Now we're going to apply our first equation for equilibrium. Normally all the forces in the x direction must add up to give you 0. Looking at our free body diagram, we only have one horizontal force, which is HB. It's pointing to the right, therefore it's positive. For equilibrium, it must equal 0. So our first reaction force, HB, is a value of 0. Now considering forces in the y direction, we have 2 point loads, UDL, and we have 2 reactions, VB and VE. Writing down our forces, we've got VB upwards positive plus VE positive going upwards minus the 2 kilonewtons point load. Then from the UDL we have 6 kilonewtons per meter. It's stretched over a distance of 3 meters, so that'll give us a total weight of 18 from that, and we have an 8 kilonewton point load on the end. They're acting downwards, therefore are negative. When we add up all our forces, they must equal 0. Rearranging this, VB plus VE minus 2 minus 18 minus 8 equals 0. Combining the numbers together, we get minus 28, and take the minus 28 to the other side of the equal sign, becomes positive 28. So we have our equation here, VB plus VE is equal to 28 kilonewtons. Next, we're going to consider moments about a point. For equilibrium, they must also be 0. Remember, moments are a force by a distance, and we must state which point we're taking moments about. So looking back at our free body diagram, we're going to take moments about our first support, which is labelled point B. So we're going to have point B, we're going to take moments about point B, and we're going to look at our free body diagram and look at the forces and the distances involved. So first of all, starting off with the 2 kilonewton point load, the distance involved for our new 2 kilonewton point load would be a distance of 1 meter. So the moment produced in that case will be 2 times 1. For the UDL, we concentrate all of the weight of the UDL. So the UDL is 6 kilonewtons per meter. It's stretched over 3 meters. So the total weight from the UDL is 18 kilonewtons, and we position that in the center of the UDL. Distance from B to the center of the UDL is 1.5 meters. Moment produced will be 18 times 1.5. Next one we're going to look at will be the force or reaction VE. The distance from B to VE is a distance of 3 meters. So the moment produced will be VE times 3. And finally, then the 8 kilonewtons on the end. The distance from point B to the 8 kilonewtons is a distance of 4 meters. So our moment equation will become 2 times 1, 2 kilonewtons, 1 meter away. The UDL, 18 kilonewtons is the total weight. Distance to its center is 1.5 meters. The reaction VE was 3 meters away from point B. And finally, the 8 kilonewtons on the end, it was 4 meters away. For equilibrium, all our moments must add up to give us 0. We'll look back at our free body diagram and consider which ones are clockwise, anti-clockwise, and hence we will be able to put in a plus or minus sign in front of each of our sets of brackets. So here, 2 kilonewtons. Imagine if it were on a piece of string. You're holding a piece of string, imaginary piece of string, at point B. How would the 2 kilonewtons rotate around point B? It would want to rotate around in an anti-clockwise direction, therefore it would be a negative moment. HB, VB don't produce a moment because they're acting at the point. Next, consider the 18 kilonewtons from the UDL. Again, imaginary piece of string holding it at point B. How would the 18 kilonewtons want to rotate around point B? It would want to rotate around in a clockwise direction, therefore it would be positive moment. VE. Again, imaginary piece of string holding that piece of string at point B. How would the VE force rotate around point B? It would want to rotate around in an anti-clockwise direction, therefore it would be negative. And finally, for the 8 kilonewtons, again, an imaginary piece of string holding one end at point B. The 8 kilonewtons allowed to freely rotate around. It would want to rotate around in a clockwise direction, therefore it would be a positive moment. Updating these values or signs into our equation. So the first one, 2 kilonewtons, that was a negative moment. The 18 kilonewtons from the UDL, that was a positive. The reaction VE, that was a negative moment. And the 8 kilonewtons on the end was positive. Simplifying down our expression, we get minus 2 plus 27 minus 3 VE plus 32 equals 0. Combine together our numbers, so we get 57 minus 3 VE equals 0. 57 is equal to 3 VE. Divide through by 3. You get the value for VE, and that's going to be 19 kilonewtons. Now going back to our earlier equation, VB plus VE is 28. We can substitute in our value for VE to be 19. So VB plus VE is 28. VB plus 19 equals 28. Take the 19 to the other side, comes negative. Work that out, and you get VB to be 9 kilonewtons. So our answer for the reactions are HB equals 0, or VB is a value of 9 kilonewtons, and VE is a value of 19 kilonewtons.